In this tutorial, we are going to cover the basics of nuclear chemistry. The first thing we will talk about is what the heck is nuclear chemistry. The second thing we will discuss are what are the forces that are acting on the nucleus of every atom. The third thing is what makes a nucleus stable versus unstable. And then the last thing we will talk about is what a radioactive element is. So, nuclear chemistry is the study of changes in the nucleus of an atom. So when we talk about nuclear chemistry, we are only focusing on the protons and neutrons only. We are not going to talk about what happens with the electrons outside of the nucleus because they're not a part of the nucleus, therefore they're not included in nuclear chemistry. Okay, so let's move on to number 2, what are the forces that act on the nucleus of an atom? Well, there are a bunch of fundamental forces in nature. Gravity is one of them. And one of them is also something called the electromagnetic force, or EMF. And the electromagnetic force is the force that causes negative things and positive things to actually be attracted to each other. So it could be a force of attraction. But it's that same force that causes things that are of like charges, for instance, 2 protons or perhaps 2 electrons, to actually be repelled by each other. So they want to get away from each other. So if you think about it, you look at the nucleus of an atom, you've got protons and you've got neutrons. Neutrons are neutrally charged, protons are positively charged. So in the nucleus of an atom, the protons are trying to get away from each other, which means that the electromagnetic force inside that's acting on the nucleus of an atom is actually a force of repulsion. So the nucleus shouldn't exist, and we know that it does. I mean, the nucleus should actually just crumble and never exist in the first place because of this electromagnetic repulsion that's taking place between the protons. So why does the nucleus exist? There must be some other force acting on it that's keeping it together. That force is called the strong nuclear force, sometimes referred to as the SNF. So again, you've got these protons that are affected by the electromagnetic forces of repulsion in the nucleus. And we know that the nucleus is really dense, right? The nucleus is dense and it's tightly packed. And it's really, really small, which implies that those particles are actually holding on to each other pretty tightly. And that force that they're holding on to each other with is a much stronger force than the electromagnetic force that's trying to push them apart from each other. So that force of attraction is called the strong nuclear force. And the strong nuclear force is actually a stronger force than electromagnetic force. In fact, the strong nuclear force is the strongest force in nature. You don't find a stronger force in nature. That's why splitting the atom was such a big deal, because that energy that's released when you break that strong nuclear force is a huge amount of energy. I mean, imagine an atomic bomb, right? That amount of energy that is released is enough to, destroy small cities. Now, there's one little caveat to the strong nuclear force. The strong nuclear force only acts across short distances. And by short distances, I mean, like the width of a neutron. Meaning that if you get too much space between 2 neighboring protons, so let's say you have 2 protons, and then in between those 2 protons, you have a lot of space, like a couple of neutrons or more, then what happens is the electromagnetic force actually takes over. And the strong nuclear force isn't strong enough to override it. And then the nucleus actually breaks apart. And when that nucleus breaks apart, that's when you've got radioactive elements. So the neutrons are there to sort of, give the right amount of space between the two protons, because if the two protons are too close to each other, then they'll just fly apart. So the neutrons are sort of like the glue that holds the nucleus together. It gives the exact right amount of space between neighboring protons to allow those protons to be attracted to each other through the strong nuclear force, and that will override the electromagnetic repulsion that they have with one another. So just remember that the neutrons serve a function. They're sort of the glue in the nucleus. Okay, so now we're going to move on to question number 3 that we introduced at the beginning, which is what makes a nucleus stable or unstable? So we just got done talking about the strong nuclear force providing this force that holds the the protons together within the nucleus, right? And so that it's this force of attraction that sort of glues the nucleus together or holds the nucleus together, even though there is a force of repulsion between the two protons because they're both the same charge. So a nucleus is stable if the distance between those two protons is like this perfect distance where the strong nuclear force can take over. And the neutrons provide that perfect distance. So if there are too many neutrons in the nucleus, then there's too much space between neighboring protons. So that strong nuclear force can't act on them, and the electromagnetic repulsion between the protons sort of takes over. So, you've always got this push and pull between the protons, and if you get too much distance between them, then the electromagnetic force wins. It's like a nuclear rock, paper, scissors, if you will, wins, and then, the nucleus becomes unstable, which means that it becomes crumbly. It wants to break apart. Another name for that is radioactive. A radioactive element is an element that's unstable because its nucleus doesn't want to stick together. The strong nuclear force is not strong enough to override the electromagnetic force. So there's another thing that would actually make the nucleus unstable besides too many neutrons. And that would be too few neutrons. So if you have too little space between the protons, the EMF just automatically takes over because that strong nuclear force only acts over this particular distance. And then, of course, the same thing would happen, and the nucleus would become unstable, or like I said, radioactive. In fact, there's sort of a perfect ratio, especially in the lighter elements, of neutrons to protons. And that perfect ratio is if you have a 1-to-1, so neutron to proton ratio, if that's equal to 1-to-1, especially in the lighter elements, then you end up having this really perfect ratio between protons and neutrons. So we're looking for somewhere near a 1-to-1 ratio, especially in the smaller elements. Okay, so that brings us to our last question, which is what is a radioactive element, which I just covered. A radioactive element is an atom whose nucleus is unstable because it either has too many or it has too few neutrons. So when you have a radioactive nucleus or a radioactive atom, what happens is that its nucleus is going to want to break apart over time. This is called radioactive decay. This radioactive decay happens over time, meaning that For some elements, it actually happens, for some radioactive elements, really quickly, and for others, it takes actually billions of years for it to happen. That process of radioactive decay is actually completely natural. You can't stop it. It just happens. There's nothing you can do to stop it. And when this nuclear decay happens, when the nucleus breaks apart to become more stable, it's either going to give up pieces of itself or it's going to emit energy or both. And those things are called radiation or radioactive particles. And we're actually going to talk about the types of radiation that atoms can undergo when they're radioactive and their nuclei are trying to become more stable. So at this point, I'd actually like to talk a little bit about something called the band of stability. So I'm going to minimize this, and we'll talk about the band of stability. So this graph right here is called the band of stability. And the way that you read this graph, for example, if we're looking at an element with, say, a proton number of 40. And if you look on your periodic table, you'll see that that's the element zirconium. Well, if you come and look and you follow this up to a proton number of 40, you'll notice that there are actually something like 1, 2, 3, 4 dots there for zirconium. Let me erase this and kind of show you what I mean. Okay, so the 4 dots for zirconium are these 4 dots right there. Perfect. So zirconium has 4 isotopes. And those 4 isotopes are in this little band right here that we call the band of stability. So it has 4 isotopes that are stable. And those stable isotopes, they actually, if you follow them over, so again, if we're looking at zirconium's 4 little dots right here and we follow them over, we can see that they range in number of neutrons. Sorry, that's not a very dark color, but hopefully you can see it, of between, say, 40 to maybe 45 or 50 neutrons. So once you get above or below that number, so once the number of protons becomes, or sorry, of neutrons, if the number of neutrons becomes greater than, say, around 45 or less than 40, then you're outside of the band of stability, and that isotope, those isotopes of zirconium become unstable, and those are radioactive isotopes. So basically the band of stability is just a graph that shows you all the stable isotopes of an element and sort of gives you an idea of the ratio that you're looking for of protons to neutrons. So for zirconium, if you've got 40 protons, because that's what makes zirconium, and you have a ratio of neutrons from around 40 to 45, then you've got a nice ratio that makes zirconium those isotopes of zirconium very stable. Anything outside of that is where you start getting into your unstable nuclei. Now, there's one last thing I want to talk about on this graph, and that's this line right here. So that line right here represents a proton to neutron ratio of 1 to 1. So when you have a 1 proton to 1 neutron ratio in your nucleus, you'll notice that down here in the lighter elements, right, the elements that have say 20 to 35 protons and the same number, 20 to 35 neutrons, that 1-to-1 ratio works really well for them. But the heavier that the the atoms become, so the heavier the elements, right, when we're getting up here to really large atomic numbers, you'll notice it deviates a lot more from this line. So the heavier an element gets, the more neutrons those elements want to have to sort of override this strong electromagnetic repulsion. I mean, if you think about it, it makes sense, right? The more protons, the more electromagnetic force you're going to have acting on the nucleus. Therefore, the more neutrons you're going to want to sort of hold those protons together. So that brings us to the end of our presentation on nuclear chemistry. And next up, we will actually be talking about the types of nuclear decay and types of radioactivity.